A stubborn structural conflict exists in mathematical topology. When mapping discrete, localized integer sequences directly onto continuous infinite fields, the models break down right where the two frameworks intersect. To analyze these intersections, mathematicians use classical fractional calculus. But applying continuous fractional derivatives to a sequence of discrete steps inevitably forces the equations to output unresolvable, non-terminating transcendental fractions. This resulting mathematical noise creates a massive analytical drag. Because the boundary between discrete steps and continuous fields cannot be resolved into a clean integer or simple fraction, the topology remains uncomputable. Mapping universal topology requires crossing that gap. To understand how geometric space functions at both the localized and infinite scale, we require a frictionless mathematical bridge between integer nodes and continuous space. Steve Konrad and Ryan Charmley propose a formal solution through an ontology called the theory of infinity, or TOI. TOI is a mathematical framework postulating that stable structures are extracted from a boundless totality via an invariant operator of symmetry. Under this framework, the mathematical universe does not generate noise by chance. It possesses highly ordered, self-correcting symmetries that isolate and preserve stable structures. Konrad and Charmley formalized this self-correcting structural symmetry into what they call the Vieta annihilation theorem. By taking a continuous fractional derivative and applying it specifically to a localized discrete Fibonacci state, the resulting mathematics do not shatter. The geometry distills itself into a computable hybrid of continuous and discrete parameters. This equation shows the Riemann-Liouville derivative applied to a discrete polynomial. The Riemann-Liouville derivative is a continuous fractional operator generalizing standard calculus using the golden ratio, phi. The resulting fraction is immediately saturated with continuous gamma functions. Expanding these terms generates massive mathematical friction, multiplying outward into an increasingly dense and complex cascade of variables. In standard analytical frameworks, this density of cascading gamma functions marks the limit of the calculation. It is the mass where classical continuous mathematics cannot cleanly interface with discrete roots. However, the golden ratio contains a specific recursive geometric property, phi squared equals phi plus 1. Substituting this specific recursive geometry directly into the dense saturated gamma expansion triggers a perfectly tuned algebraic chain reaction. The expanded gamma terms collapse into pure powers of phi, scaled exclusively by the square root of 5. We can then factor out the common gamma expression, completely erasing the continuous transcendental friction. Konrad and Charmley term this gamma annihilation. Leveraging golden ratio symmetry forces the continuous derivative to shed its non-terminating fractions, leaving an exact closed-form equation. To locate the absolute limits of this cleaned polynomial, we anchor it to a specific discrete step. By evaluating the system at rung 10, where the Fibonacci number is 55, we can examine its localized state. This equation shows the manifest configuration. It is an all-positive derivative polynomial, stripped of the sign alternating decay that usually destabilizes classical sequences. To analyze the holistic topological mass of this specific phase space, we apply Vieta's formulas. These algebraic rules define the exact relationships between a polynomial's coefficients and the sums and products of its roots. Theorem 3.1 derives the spatial boundaries for the sum of the roots, denoted as S. Plugging the discrete Fibonacci coefficients into the Vieta formula simplifies the polynomial representing the linear mass. Theorem 3.2 executes the same extraction for the product of the roots, or P. Substituting the coefficients isolates a clean, exact boundary for the volumetric mass. These two isolated parameters are no longer endless strings of transcendental noise. They represent the closed-form algebraic values for the system's total linear mass and its volumetric mass. This equation represents the Konrad-Charmley ratio operator. By dividing the absolute value of the sum by twice the product, the operator pits continuous linear mass directly against fractional volumetric space. The moment these parameters are combined, structural cancellation begins. The continuous topological mass, the square root of 5, and the scalar constants mathematically annihilate one another, perfectly canceling out. Finally, the ancestral discrete base node cancels out from both sides. All friction is structurally annihilated. the complex continuous formula collapses down into a pristine spatial matrix. The operation isolates a simple discrete integer fraction, scaled by a volumetric golden tensor, phi cubed. It is free of continuous noise. We have a clean hybrid matrix for a localized rung, but to prove its universality, we must evaluate the absolute continuous limit as the sequence rung approaches infinity. This equation calculates the continuous limit. As n approaches infinity, the fractional ratio of f sub n minus 2 over f sub n resolves to phi to the power of negative 2. Multiplying phi to the negative 2 by the golden volume of phi cubed resolves the exponents. This reduction returns a single power of the golden ratio. In an idealized infinite continuum, the discrete structural mass cancels its own fractional geometry. It sheds the continuous mathematical drag to return exactly to the limit of the golden set. This diagram shows the difference between evaluating the limit at infinity, which yields roughly 1.618034, and the empirical evaluation of rung 10, which yields 1.61738. Subtracting the finite state from the infinite limit reveals a gap of 0.000654. Under TOI ontology, this specific numeric gap is the beta effect, or topological friction. The beta effect shows that discrete sequences are distinct mathematical states. In this framework, the continuous manifold functions as their idealized, frictionless limit. This value quantifies the mathematical tension required for the golden set to anchor a finite, discrete rung 10 state inside a continuous, infinitely scalable volume. The Vieta annihilation theorem formalizes the mechanism that stabilizes continuous discrete topology. It demonstrates that localized integer sequences and the infinite properties of calculus are mathematically resolvable. While classical calculus generates geometric friction when applied to non-integer steps, the system contains a self-correcting mechanism to shed this exhaust. Discrete integer structures act as the anchors that regulate and eventually annihilate the continuous fractions of reality, maintaining a stable topological system.